Welcome to This Explainer. Today, we're diving into something that's a total game changer for AI infrastructure. We're unpacking Turbovec. It's a seriously impressive Rust-based vector index that directly tackles one of the most frustrating bottlenecks in local AI development right now, the massive memory wall. To really get why this matters, picture this. You're building a local, private application. Let's say it's an AI assistant strictly for your company's highly sensitive internal documents. You've got a corpus of about 10 million documents. If you try to store those as standard float32 vectors, those highly precise numbers that just gobble up digital real estate, you're suddenly looking at needing 31 gigabytes of RAM just for storage alone. For most local setups, or even small cloud servers, handing over 31 gigs purely for an index, that's an absolute deal breaker. But what if you could take that exact same dataset and crush it down to a mere 4 gigabytes? That's a 16x compression. And the best part? You're doing this without losing search speed and without sacrificing a drop of accuracy in your results. Well, that is exactly what Turbovec brings to the table. Here's our roadmap for this explainer. First, we'll cover the vector memory problem. Then, introducing Turbovec. Third, decoding the TurboQuant algorithm. Fourth, beating the benchmarks. And finally, plug-and-play RAG. All right, part one, the vector memory problem and the hidden costs of standard vector databases. Let's be honest, the old way of building vector databases is honestly a headache. You're usually stuck relying on expensive managed services or wrestling with super tedious workflows. We're talking heavy training steps, constant index rebuilds every time your data grows, and that super annoying overfetching or the system pulls way more data than you need, forcing you to filter it down manually. The Turbovec way completely flips this. It gives you instant online ingest. You literally just add vectors and boom, they're indexed. No training step. Plus, it operates as a pure local, air-gapped solution right on your machine, so your private data stays exactly that, private. Which brings us to part two, introducing Turbovec. It's the scrappy, pure local Rust index taking on the industry giant FAISS. Turbovec is this incredibly lightweight powerhouse, and its secret weapon is actually Google Research's TurboQuant algorithm. The source defines this as a data-oblivious quantizer with near-optimal distortion. Now, in plain English, data-oblivious just means the algorithm doesn't need to study your specific data beforehand to figure out how to compress it. Because of that, it totally eliminates the need for any separate time-consuming training phase. But how does it actually do that? Let's get into part three, decoding the TurboQuant algorithm. We're going to look at how math acts as a predictable rotation and packing process. The whole thing hinges on this one foundational truth. After applying a random rotation, every coordinate follows a known distribution, regardless of the input data. This is the brilliant insight that makes Turbovec tick. By mathematically rotating the vectors, it ensures the math works perfectly and efficiently, no matter how weird or unstructured your input data is. There are 6 specific steps where this magic actually happens. It's a really clever mathematical sequence that groups similar directions together to save massive amounts of space. Let's break these down in pairs to see what's actually happening under the hood. Steps 1 and 2 are normalize and random rotation. First, the algorithm strips the length from each vector, storing it as a single float. This leaves every vector as a unit direction on a high-dimensional sphere. Think of it kind of like scrambling a Rubik's Cube, but instead of random twists, you're using a highly specific set of mathematical moves, so the outcome is always totally predictable. It multiplies all vectors by the exact same random orthogonal matrix. So by normalizing and rotating, it guarantees every single coordinate independently follows a known beta distribution. Basically, it forces the messy unknown of your data to conform to a perfectly predictable shape. Moving right along to steps 3 and 4, calibration and quantization. At finite dimensions, coordinates can sometimes drift just a little bit, so the TQ plus calibration step fits a simple shift in scale during the very first add to snap those coordinates right back into place. It calibrates once, never needs retraining. Then Lloyd max quantization kicks in. This is essentially ultra-smart bucketing. Since the algorithm now knows the exact distribution of our numbers, it can perfectly pre-compute the absolute best way to group or bucket the coordinates. You get 4 buckets for 2-bit quantization or 16 buckets for 4-bit. It's pure universal math, completely independent of the specific documents you uploaded. Finally, steps 5 and 6, bit pack and score. This is where we see that massive space savings. It takes these perfectly bucketed little integers and packs them incredibly tightly into bytes, giving us that stunning 16x compression. A massive 1,536-dimensional vector literally drops from over 6,000 bytes down to just 384 bytes. Now, normally, compressing vectors creates a downward mathematical bias that really messes up your search scores. But step 6 fixes that entirely. Turbovec computes a length-3 normalized score at encode time. It fixes the bias at the exact moment of compression, so you get completely unbiased accuracy later with literally zero extra search time cost.
Now for part 4, beating the benchmarks. David takes on Goliath. Let's see how this scrappy Rust index holds up against Meta's industry-standard FAISS library.
The performance numbers here are frankly incredible. On ARM architecture, specifically the Apple M3 Max, Turbovec uses handwritten neon kernels for fast SIMD search. Thanks to this deeply optimized hardware-level math, Turbovec flat-out beats FAISS FastScan by 10 to 19% across every single configuration tested. And it's not just ARM. On x86 machines, it totally holds its own, winning by up to 5% on 4-bit configurations. It only modestly trails on 2-bit, where FAISS has a slight hardware path edge. But the most crucial metric here is the recall accuracy. Across standard OpenAI dimensions of 1536, Turbovec consistently beats FAISS by 0.2 to 1.9 points at recall at 1. That means it is significantly better at grabbing the absolute most relevant document and putting it in the exact #1 search spot. It's faster and it's more accurate. Let's wrap up with part 5, plug-and-play RAG, frictionless adoption for your pipelines. The absolute best part about all of this is that you do not need to rewrite your whole architecture to get these massive memory and speed benefits. Turbovec provides Python bindings that act as pure drop-in replacements for the most popular frameworks out there. LangChain, LlamaIndex, Haystack, Agno, it's literally just a simple pip install. You keep the exact same public surface and retriever wiring, you just swap the import and you're good to go. It even handles metadata filtering completely seamlessly. The filtering happens right inside the SIMD kernel at a 32-vector block granularity. So if your filter says a block isn't allowed, it's instantly short-circuited before any scoring work is even attempted. You get exact result lengths, zero overfetching, and absolutely no padded fallbacks. It totally bypasses the recall hit that you almost always see in other vector stores. So I'm going to leave you with this final thought. If a pure local open-source tool can match or even beat the industry giants in speed and accuracy, all while cutting your RAM requirements by a massive 16x, why on earth are we still exposing our private data to external managed services? This explainer really shows that high-performance, private, air-gapped AI search is completely accessible to anyone right now. It definitely makes you rethink your entire approach to vector databases, doesn't it? Thanks for diving into this fascinating tool with me, and keep exploring.